Hi there, this is Mary. I'm a software engineer and also a Rust engineer. Welcome to the second video of this Rust series. In this video, we're gonna go over the most important and unique feature of Rust, the ownership. We will also understand the borrow checker and how stack versus heap works. We will try to understand references, slices, and also move semantics, and some of the other things along with it. We will also get a little bit of intro to lifetimes. I am super excited for this journey. I know some of the topics might seem super new, but stick with it. It might seem scary, but it's not. After all, we're gonna go through this journey together. I don't expect you to know having prior or any Rust knowledge. So let's go and dive into it. If you have heard about Rust, you have definitely heard about ownership. Everything we do today with Rust flows from this one idea. Here's why. Before we dive in what's ownership, we need to understand what this is. Well, ownership is a different way to manage memory. It's how Rust manages memory. Every value has a clear owner. While most languages use garbage collection, it cleans up the memory for you. It's easy, but you lose control and speed because the garbage collector is itself a huge chunk of code. There's also a manual memory management, for example, languages like C. But you have to free memory yourself, and there can be errors everywhere. But Rust picks up a different way to manage memory. And if for this way, the compiler enforces a rule at the right time, which is fast and safe. But it's also a learning curve. Well, there's ownership. Now let's go ahead and see where the data actually lives. Memory in your program lives in two places, the stack and the heap. The stack is like a stack of plates. You push values on top and pop them off the top. Last in, first out. The stack holds small things whose size is known when you write the code. Numbers, booleans, simple structs. Push and pop are fast because the position is fixed. The heap is the messy room. The allocator finds free space, returns a pointer. The pointer sits on the stack, but the data sits on the heap. The heap holds things that can grow while your program runs. Text, list, anything whose size you don't know when you write the code. Stack data is cleaned up automatically when the scope ends. Heap data needs an owner. Well, that's why the ownership exists, cleaning up the heap safely. Before we go deeper into Rust and ownership, we need to know three rules of ownership. These are what the compiler actually checks. If you remember, let's say nothing else from this video, at least remember these three rules which Rust compiler actually checks. Rule number one, every value in Rust has exactly one owner. An owner is just a variable that holds the value. When you create a string and store it in a variable, that variable is now the owner of that string. Rule number two, only one owner at a time. A value can move from one variable to another. and the ownership goes with it, but never two owners at once. Now, last but not least, rule number 3. When the owner goes out of scope, the value is dropped automatically. Dropped means Rust runs the cleanup, frees any heap memory it was using, all of it automatically. No garbage collector, no manual freeing the memory. Well, you have already seen all 3 in action, the stack versus heap explanation part. That was rule 3 working quietly. Now the rules have names. Well, that's it. The 3 rules. Everything else in Rust is the compiler enforcing them. A string lives on the heap. That's where things that can grow live. I bet you remember that. Well, here's a string. Rust puts the letter on the heap and a pointer to these letters on the stack. Let's take a closer look into this. Now write let tag equals to cat name. In most languages, the second variable would be a copy of the first. But in Rust, this is a move. Ownership transfers from cat name to tag. The heap data isn't copied, just the pointer on the stack moves over. If you try to use cat name after the move, the compiler stops you right at the compile time before your program runs. But the tag variable works. It's the new owner of the heap data. Move semantic rules out 2 classic memory bugs: double free, which is freeing the same memory twice, and use after free, which is reading memory after it's already been freed. Just one owner at a time, so neither can happen. That's how Rust gives you the speed without the bugs. In the last part, when we used move, it actually broke the variable cat name. But what if we actually need both of them? Well, in that case, we can use clone. It's a method you can call by hand. Rust allocates a new heap memory for the second variable and copies the bytes over. It's actually slower than a regular move, but you wrote the clone method, so you know it's happening. Now, the catname variable still has its string, and the tag has its own copy, 2 pointers to heap, and of course 2 owners. Now for the stack data, integers, boolean characters, these have a small fixed size, so copying them is really cheap. Rust just duplicates the bits. No clone is needed for this. Rust calls this copy type. Any value purely on the stack qualifies for this. All integers, float types, boolean characters, and tuples, where every piece is also copy. Stack types, copy, heap types, move, or opt into clone. So that's it. Moving the ownership doesn't only happen in the cases of variables by using let. It also happens at function boundaries too. Here's a function. It takes a string, prints a greeting, and returns the string. When you call it, the kitten string moves into the function. Same mechanic as before. The heap data isn't copied. Ownership just transfers from kitten to the function's name parameter. Try to use the kitten again. Well, you'll get compile errors. Same rule as before. But the function returns the string and the ownership transfers back into the back again, which is the new owner. function move ownership in and can move it back out. And that's it. Sometimes you need a function to read a value or change it, but you want to keep the ownership in the caller. Well, in that case, move might lose it and clone could be wasteful for the memory. But the solution of this is actually passing a reference. The ampersand symbol means borrow. A reference is a pointer to the data, not the data itself. The function reads through it. The caller still owns the value the whole time. Now, shared reference is read-only. Many readers can share the same value at the same time because none of them is changing it. No conflict can be possible for this case. But what if you need to change the data through the reference? Well, in that case, you can use mutable reference by using this ampersand and mute keyword. For mutable references, you can read and write, but only one at a time. Two writers could step on each other, or a reader could see half a change, and Rust prevents this entirely. While share to read and mute to change, the original owner keeps the data. The borrow checker is what Rust uses to enforce reference safety. It has two rules. Let's learn them, and most errors actually make sense. Rule number 1: at any time you can have one mutable reference or many shared references, but not both. This rule prevents two writers from clashing or a reader from seeing half a change. Many shared references work. One mutable works. Mixing them or having two mutable at once does not. Rule number 2: references must always be valid. A reference that points at something that's gone is called a dangling reference. Rust won't let you create one. Here, the saved borrow cat age, but cat age goes out of scope at the closing brace. So the saved would be left dangling. The compiler stops you before that can happen. Well, that's it. Two rules. Together they rule out data races and dangling references at compile time. Sometimes you don't want the whole thing, or the whole portion of it, or maybe you want just a slice or a little bit of the portion. Well, in that case, we can use range with ampersand. There are two indices, where the slice starts and where it ends. A slice is a reference, not a copy. Here, first is the first 5 characters of cat name, and last is the rest. No new heap memory, both are references that points into the original. Same syntax works on arrays. This gives you a slice into the first 2 items. Different sequences, but the same idea. Slice follows the borrow rule because they reference the original. The original can't disappear while the slice is still alive, otherwise the slice would dangle. Slices is a new view into a part of a thing, references with a bound. What type should a function take for a string parameter? Well, quick refresher. String is the owned global type that lives on the heap. But this string slice is a reference to a string data. A slice. Here's a flexible which takes a string slice. Both calls actually work. The first passes a reference to an owned string. The second passes a string literal, the text you wrote right in your code. Both fit the string slice. Now let's compare this strict same body, different parameter, and string reference. Now the literal call fails. A literal isn't an owned string, so the type doesn't match. It's also less flexible. If you need an owned string later, convert it with this, the to string or to owned. All three does the same thing. Take a string slice to read. Take string only when you need to own the data. Do you remember the rule number 2? That the reference must always be valid. Well, there's a name for that rule. It's called a lifetime. Every reference has one. The lifetime is the span of code where that reference is allowed to exist. Watch cat name is born here. The label borrows it. When the closing brace runs, both go out of scope at the same time. Label cannot live past cat name. Same rule as the dangling references from the borrow checker. The compiler is preventing one. Now you know the name for it. Sometimes Rust cannot figure out the lifetime relationship on its own. Then you label it yourself by using this tick. So we're using this tick A, it's just a name. Here it says the input and the output share the same lifetime. We're gonna go deep into this in one of the next videos. But for now, lifetime is just how long a reference is allowed to live. One owner, always. Everything else in Rust follows from this. And that's all for the ownership part. In the next video, we're gonna go over making your own types, struct and enums together. See you on the next one. Thank you so much for watching.